more powerful than single-chip MOS microprocessors such as the 1972 Intel 8008 until the early 1980s. 21. Advances in IC technology, primarily smaller features and larger chips, have allowed the number of MOS transistors in an integrated circuit to double every 2 years, a trend known as Moore's law. Moore originally stated it would double every year, but he went on to change the claim to every 2 years in 1975. 35. This increased capacity has been used to decrease cost and increase functionality. In general, as feature size shrinks, almost every aspect of an IC's operation improves. The cost per transistor and switching power consumption per transistor goes down, while the memory capacity and speed go up through the relationships defined by Dennard scaling, MOSFET scaling. 36. Because speed, capacity, and power consumption gains are apparent to the end user, there is fierce competition among the manufacturers to use finer geometries. Over the years, transistor sizes have decreased from tens of microns in the early 1970s to 10 nanometers in 2017. 37. With a corresponding million-fold increase in transistors per unit area. As of 2016, typical chip areas range from a few square millimeters to around 600 millimeter to, with up to 25 million transistors per millimeter. 38. The expected shrinking of feature sizes and the needed progress in related areas was forecast for many years by the International Technology Roadmap for Semiconductors, ITRS. The final ITRS was issued in 2016, and it is being replaced by the International Roadmap for Devices and Systems. 39. Initially, ICS were strictly electronic devices. The success of ICS has led to the integration of other technologies, in an attempt to obtain the same advantages of small size and low cost. These technologies include mechanical devices, optics, and sensors. Charge-coupled devices, and the closely related active pixel sensors, are chips that are sensitive to light. They have largely replaced photographic film in scientific, medical, and consumer applications. Billions of these devices are now produced each year for applications such as cell phones, tablets, and digital cameras. This subfield of ICS won the Nobel Prize in 2009. 40. Very small mechanical devices driven by electricity can be integrated onto chips, a technology known as microelectromechanical systems. These devices were developed in late 1980s, 41, and are used in a variety of commercial and military applications. Examples include DLP projectors, inkjet printers, and accelerometers and MEMS gyroscopes used to deploy automobile airbags. Since the early 2000s, the integration of optical functionality, optical computing, into silicon chips has been actively pursued in both academic research and in industry, resulting in the successful commercialization of silicon-based integrated optical transceivers combining optical devices, modulators, detectors, routing, with CMOS-based electronics. 42. Photonics integrated circuits that use light such as Lightelligence Space, photonic arithmetic computing engine, also being developed, using the emerging field of physics known as photonics. 43. Integrated circuits are also being developed for sensor applications in medical implants or other bioelectronic devices. 44. Special sealing techniques have to be applied in such biogenic environments to avoid corrosion or biodegradation of the exposed semiconductor materials. 45. As of 2018, the vast majority of all transistors are MOSFETs fabricated in a single layer on one side of a chip of silicon in a flat two-dimensional planar process. Researchers have produced prototypes of several promising alternatives, such as various approaches to stacking several layers of transistors to make a three-dimensional integrated circuit. 3D, such as through-silicon via, monolithic 3D, 46, stacked wire bonding, 47, and other methodologies. Transistors built from other materials. Graphene transistors, molybdenate transistors, carbon nanotube field effect transistor, gallium nitride transistor, transistor-like nanowire electronic devices, organic field effect transistor, etc. Fabricating transistors over the entire surface of a small sphere of silicon. 48, 49. Modifications to the substrate, typically to make flexible transistors for a flexible display or of the flexible electronics, possibly leading to a roll-away computer. As it becomes more difficult to manufacture ever smaller transistors, companies are using multi-chip modules, three-dimensional integrated circuits, package-on-package, high-bandwidth memory and through-silicon vias with die stacking to increase performance and reduce size, without having to reduce size of the transistors. Such techniques are collectively known as advanced packaging. 50. Advanced seed packaging is mainly divided into 2.5D and 3D packaging. 2.5D describes approaches such as multi-chip modules, while 3D describes approaches where dies are stacked in one way or another, such as package-on-package and high-bandwidth memory. All approaches involve two or more dies in a single package. 51, 52, 53, 54, 55. Alternatively, approaches such as 3D NAND stack multiple layers on a single D. Design. Virtual detail of an integrated circuit through 4 layers of planarized copper interconnect, down to the polysilicon, pink, wells, grayish, and substrate, green. The cost of designing and developing a complex integrated circuit is quite high, normally in the multiple tens of millions of dollars. 56, 57. Therefore, it only makes economic sense to produce integrated circuit products with high production volume, so the non-recurring engineering, NRE, costs are spread across typically millions of production units. Modern semiconductor chips have billions of components, and are far too complex to be designed by hand. Software tools to help the designer are essential. Electronic Design Automation, EDA, also referred to as Electronic Computer-Aided Design, ECAD, 58, is a category of software tools for designing electronic systems including integrated circuits. The tools work together in a design flow that engineers use to design, verify, and analyze entire semiconductor chips. Some of the latest EDA tools use artificial intelligence, AI, to help engineers save time and improve chip performance. Types. A to D converter IC in a DIP integrated circuits can be broadly classified into analog, 59, digital, 60, and mixed signal, 61, consisting of analog and digital signaling on the same IC. Digital integrated circuits can contain billions, 38, of logic gates, flip-flops, multiplexers, and other circuits in a few square millimeters. The small size of these circuits allows high speed, low power dissipation, and reduced manufacturing cost compared with board-level integration. These digital ICs, typically microprocessors DSPs, and microcontrollers, use Boolean algebra to process 1 and 0 signals. The die from an Intel 8742, an 8-bit NMOS microcontroller that includes a CPU running at 12 MHz, 128 bit ESOF RAM, 2048 bytes of EPROM, and E/O in the same chip. Among the most advanced integrated circuits are microprocessors or cores, used in personal computers, cell phones, microwave ovens, etc. Several cores may be integrated together in a single IC or chip. Digital memory chips and application-specific integrated circuits, ASICs, are examples of the families of integrated circuits. In the 1980s, programmable logic devices were developed. These devices contain circuits whose logical function and connectivity can be programmed by the user, rather than being fixed by the integrated circuit manufacturer. This allows a chip to be programmed to do various LSI-type functions such as logic gates, adders and registers. Programmability comes in various forms: devices that can be programmed only once, devices that can be erased and then reprogrammed using UV light, devices that can be reprogrammed using flash memory, and field programmable gate arrays, FPGAs, which can be programmed at any time, including during operation. Current FPGAs can, as of 2016, implement the equivalent of millions of gates and operate at frequencies up to 1 GHz. 62 analog ICs, such as sensors, power management circuits, and operational amplifiers, op-amps, process continuous signals, and perform analog functions such as amplification, active filtering, demodulation, and mixing. ICs can combine analog and digital circuits on a chip to create functions such as analog to digital converters and digital to analog converters. Such mixed signal circuits offer smaller size and lower cost, but must account for signal interference. Prior to the late 1990s, radios could not be fabricated in the same low-cost CMOS processes as microprocessors. But since 1998, radio chips have been developed using FMOS processes. Examples include Intel's DECT cordless phone, or 802.11 Wi-Fi chips created by Atheros and other companies. 63. Modern electronic component distributors often further subcategorize integrated circuits. Digital ICs are categorized as logic ICs, such as microprocessors and microcontrollers, memory chips, such as MOS memory and floating gate memory, interface ICs, level shifters, serializer /deserializer, etc., power management ICs, and programmable devices. Analog ICs are categorized as linear integrated circuits and RF circuits, radio frequency circuits. Mixed signal integrated circuits are categorized as data acquisition ICs, including A// converters, D// converters, digital potentiometers, clock / timing ICs, switched capacitor, SC circuits, and RF CMOS circuits. Three-dimensional integrated circuits, 3D ICs, are categorized into through-silicon via TSV, ICs and CU/CU connection ICs. Manufacturing. Fabrication. Rendering of a small standard cell with 3 metal layers, dielectric has been removed. The sand-colored structures are metal interconnect, with the vertical pillars being contacts, typically plugs of tungsten. The reddish structures are polysilicon gates, and the solid at the bottom is the crystalline silicon bulk. The semiconductors of the periodic table of the chemical elements were identified as the most likely materials for a solid-state vacuum tube. Starting with copper oxide, proceeding to germanium, thin silicon, the materials were systematically studied in the 1940s and 1950s. Today, monocrystalline silicon is the main substrate used for X, although some 3D compounds of the periodic table such as gallium arsenide are used for specialized applications like LEDs, lasers, solar cells and the highest speed integrated circuits. It took decades to perfect methods of creating crystals with minimal defects in semiconducting materials. Crystal structure. Semiconductor ICs are fabricated in a planar process which includes 3 key process steps: photolithography, deposition, such as chemical vapor deposition, and etching. The main process steps are supplemented by doping and cleaning. More recent high-performance ICs may instead use multigate FIN-FET or GaA-FET transistors instead of planar ones, starting at the 22 node, Intel, or 16/14 nm nodes. 64. Monocrystal silicon wafers are used in most applications, or for special applications, other semiconductors such as gallium arsenide are used. The wafer need not be entirely silicon. Photolithography is used to mark different areas of the substrate to be doped or to have polysilicon, insulators or metal, typically aluminium or copper, track